Hello Gators, this is 4.7 using L'Hopital's rule for determining limits of indeterminate forms. Let's remember what an indeterminate form is. It's when you substitute the value as x approaches a and it'll be 0 over 0. In the past, we have had these kind of indeterminate forms. For this limit, we know that limit is 1. For this, we had a technique in which we used factoring to help us eliminate the hole in the graph by reducing, and once we reduced, we went ahead and evaluated with the remaining factor, and that answer was 4. We're going to have a theorem in which we can have an alternative method in which to evaluate these limits. So what it says is if f of a and g of a is equal to 0, so we have an indeterminate form, then to find the limit, you just find the value of the derivatives at a. So in this particular case, we know that this is a 0 over 0, and we know that the derivative of sine is cosine of x. And so L'Hopital's rule says take the derivative and evaluate it at our a value, which is 0, all over. The derivative of this is 1, and so the answer is 1, which is what we got before. Over here, the derivative of the numerator is 2x, the derivative of the denominator is 1, and remember, this is an indeterminate form, otherwise we're not allowed to use it. And then the derivative evaluated at 2 will be here, and the derivative here is 1, and the answer is 4. These are the same answers that I got before with an algebraic technique. Now I'm using L'Hopital's rule. What is L'Hopital's rule graphically? What's it doing? Well, what it's really telling us that when we have this situation that the two functions are sharing the same point, and that same point's value is 0, so it's crossing the x-axis, then we know that the limit of those two functions is really the limit of the two slopes. So the slope of the function evaluated at a and the slope of the function evaluated at a, that's going to be the answer. Let's take a look at the proof. Why is this working? Well, the derivative of a at derivative of g at a is this. This is the definition of a derivative. Since they both have the same limit expression, let's make it into the whole expression with one limit. So this whole fraction now is in regards to one limit. We're going to multiply the numerator by x minus a and the denominator by x minus a, and that'll eliminate and simplify the complex fraction. Now we have this. And we know from the hypothesis of the theorem that the y values are crossing at the x-axis, so these values are 0, and therefore we have this limit. So going in a backwards way, we see that the slopes of the tangent lines at a is equal to the ratio of the two functions approaching a. All right, remember you always want to try direct substitution first. Let's take a look at this limit. If I substitute 3 into the numerator, I get 1. If I substitute 3 into the denominator, I get 3. This is not eligible for L'Hopital's rule. The answer is just 1/3. Don't think all limits are L'Hopital's rule. Let's take a look at this limit. The denominator I know is 0, and the numerator is going to be 4 take away 14 plus 10, and I can see that's going to be a 0 in the numerator. So this is eligible for L'Hopital's rule. I'm going to take the derivative of the numerator, which is 2x minus 7, and I'm going to evaluate it at 2. So everywhere there's an x, I'm going to write 2. And then the derivative of the denominator is 1, and so the answer is -3. I didn't have to go through factoring. So L'Hopital's rule, I'm going to say it one more time. As long as the f of a and g of a are 0, it's an indeterminate form. L'Hopital's rule allows you to do this. The limit as x approaches a of f of x over g of x is going to be the values of their derivatives or their slopes, f of a over g prime of a. And make sure that when you're using L'Hopital's rule, you're looking at a limit expression written in fractional form. All right, let's go ahead and take a look at these two, and then you're going to be doing some problems. We want to evaluate the numerator, and I put a 2 and a 2, so I can see that's a 0. And when I put 2 in for x in all of them, I can see that's 0 as well. So I want to go ahead and I want to find the derivative, and the derivative here is 1. The derivative of the denominator here is 9x squared minus 12x plus 1, but remember I want to evaluate it at x is equal to 2. So the answer is going to be 1 over, and then that's going to be a 36 minus 24 plus 1, and so the answer is 1/13. Over here I can see it's 0 over 0. Always make sure that you have an indeterminate form. And so the derivative here will be cosine of 6x. Don't forget the chain rule, so that'll be a 6, all divided by 1. Remember, I want to evaluate this at x is equal to 0. And when that happens, my numerator will be 6, and then denominator is 1, and I'm done. Okay, L'Hopital's rule is not the quotient rule. I know students look at quotients and they want to take the derivative of the numerator and the derivative of the denominator. That is not L'Hopital's rule. L'Hopital's rule is about limits. This is about derivatives. You must take the derivative this way. L'Hopital's rule stronger version, which is what I like to use. And it says that as long as we have the hypothesis, the same hypothesis that we had before, the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of the derivative over the derivative. I like this form because I like to continue taking the limit, and then I evaluate the limit when I feel like it. Sometimes we have to do it more than one time. Let's take a look at these problems. Some limits cannot be found using algebraic methods. If direct substitution produces a 0 over 0, or infinity over infinity, any combination, plus in the numerator, minus in the denominator, any kind of combination, the rule, L'Hopital's rule, can help you find the limit. Okay, over here, this is going to be infinity over infinity. I'm going to use the stronger version. I'm just going to write the limit as x approaches infinity, and I'm going to find the derivative of the numerator, which is 1, derivative of denominator e to the x, and now I'm ready to evaluate. And I can see the denominator is getting very large, so the whole fraction is going to 0. Over here I have an infinity over infinity again, and so I'm going to take the limit as x approaches infinity, and I'm going to take the derivative of the numerator, which is e to the x, derivative of the denominator, which is 1, and I can see the numerator is getting very large, so the answer is infinity. Over here I have a 0, and I have this value as 1. This is not eligible for L'Hopital's rule. All I have to do is I notice that substitution will work. It's 0, and then this is going to be a 1, so the answer is 0. So do not use L'Hopital's rule just because it looks like a candidate for a rule. It looks like a quotient, oh, I'm going to use L'Hopital's rule. No. Make sure that you use direct substitution and see if you produce the hypothesis that's necessary. All right, I'd like you to try it. Stop the screencast and see if you have the same answers. And here are the answers. Both of them were candidates for L'Hopital's rule, and I used the stronger version. I'm taking the limit at each step, and then only at the end am I evaluating. Let's take a look. If using L'Hopital's rule leaves you with this form 0 over 0 or infinity or any combination, it is a process which can be repeated as many times as necessary. Just remember to use direct substitution at each step to make sure the rule can be checked. So I'm going to do this problem, and I notice that the numerator is infinity, and the denominator, if I put negative infinity in here, that turns to positive infinity. E to the positive infinity is infinity. And again, I'm going to use a stronger version. I'm going to be taking the limit at each step, and then I'll evaluate later. So this is going to be 2x, and the denominator will be e to the opposite of x, but remember to take the chain rule, and that'll be a minus. So the numerator will be negative infinity, and the denominator, if I put negative infinity in here, that's going to be positive infinity, but there's a negative underneath, so that's negative infinity. All right, so I'm going to take the limit as x approaches negative infinity, and I'm going to take the derivative of the numerator, which is 2, and the derivative of the denominator will be e to the negative x. When I take the chain rule, a negative times a negative is a positive. And I'm going to see that if I put a negative infinity in here, I'm going to get a very large number, and it's going to be e to the positive infinity, which makes the fraction very small, 0. I'm going to let you do the next one. I'd like you to stop the screencast and try the problem and then turn it back on, and I'll have the answer for you. And here is the answer. And this is the end of the screencast.